Hello everyone, my name is Steven. This is my video submission for week 1 and hope you enjoy it. For this assignment, I've put together a series of video clips that highlight what I believe is important material. After each clip, I'll provide some commentary and go over the key points. Let's get started with clip 1.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural.
So for clip number 1, we have a very interesting first minute introducing the problem that neural networks are designed to solve. How can computers recognize patterns as easily as humans? The video starts by showing how humans can effortlessly recognize handwriting digits even when they are writing in different styles. This is a task that is trivial for human brains but is incredibly challenging to program for a computer using traditional methods. This leads to the motivation for machine learning and neural networks as a way to solve complex pattern recognition problems. The narrator also emphasizes that the goal of these videos is to show what a neural network actually is, not just treat it like a buzzword, but understanding it as a piece of math. The focus in the first video is on the structure of the neural network and what it means for the neural network to learn.
It's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents, or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a
So for clip 2, I decided to name it the neuron, the basic building block. This clip explains the basic unit of a neural network, the neuron. The video emphasizes that a neuron is simply a container for a number between 0 and 1. In the first layer, the network starts with neurons that correspond to the pixel of the input image. For a 28 by 28 pixel image, there are 784 neurons, each holding a grayscale value of the corresponding pixel, from 0 for black to 1 for white. These values are also called the activation of the neuron. The video goes on to describe the output layer, which for a digit recognition network has 10 neurons, one for each digit. The activation of the output neurons represent how much the network thinks the image corresponds with the given digit. The video also introduces the concept of hidden layers that are in between the input and output layers. Moving on to clip number 3.
Between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and the sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network.
For this clip, we have how layers influence each other. This clip focuses on how activations in one layer influence the activations in the next layer. The goal is to create a mechanism that can combine pixels into edges, edges into patterns, and patterns into digits. To achieve this, each connection between neurons is assigned a weight. The video introduces the idea of visualizing weights as a grid, using green pixels for positive weights and red pixels for negative weights. The activation of a neuron is determined by a weighted sum of the activations of the neuron in the previous layer. If you have mostly zero weights except in a certain region, then the weighted sum will mostly be determined by the value in that region. In addition, a bias is added to the weighted sum, which determines how high the weighted sum needs to be before the neuron becomes meaningfully active. Finally, the video introduces the sigmoid function, which squishes the sum into a range between 0 and 1.
Hi, welcome to this lecture on Universal Approximation Theorem. If you have worked in machine learning, you may have heard of this. Otherwise, you may be hearing about this theorem for the first time. This lecture is an attempt to illustratively prove this theorem. And my understanding is that if you truly understand Universal Approximation Theorem, you have a very good intuition for why machine learning or neural networks are able to do such powerful things that it is capable of doing. So technically, this is not in the strict sense, this is a proof, but this is more like an illustrative demonstration or a way for you to be convinced of the validity of this theorem. So my name is Dr. Sridhar Panat. I'm a PhD from MIT. And in this lecture, we'll be going through this theorem with a very specific example. So let's
To the universal approximation. This video introduces the universal approximation theorem, which is a key concept for understanding how neural networks can accomplish complex tasks. The theorem states that a feed-forward neural network with just one hidden layer and a finite number of neurons can approximate any continuous function within a subset of input values with a degree of accuracy that depends on how many neurons you have in the hidden layer. The key requirements are a feed-forward network, single hidden layer, a finite number of neurons, and a continuous, non-constant, and bounded activation function. The speaker clarifies that the video will illustrate rather than strictly prove the theorem. The speaker also states that if you truly understand the universal approximation theorem, you have a good intuition for why neural networks are able to do such powerful things. Moving on to the next clip.
is non-constant, it is continuous, and it is bounded. There are so many different terms here, and that's the reason why I have made most of them, or most of the important ones, in bold and underline: feed-forward neural network, single hidden layer, finite number of neurons, etc. So don't be overwhelmed if you cannot visualize this theorem really well. Basically, in simple sense, what it is saying is, using discrete set of items, you can kind of approximate a continuous function or anything that is continuous, and the degree of accuracy will depend on how many discrete items you are chopping this whole thing into. You may be familiar with this idea if you have done integration, numerical integration, as you can see in this picture. But what the universal approximation theorem is saying essentially is something like this. You can think of neural network as function approximators. And let's see if this is true.
For the second to the last clip, it begins the explanation of the universal approximation theorem by using the example of approximating a complex function with a series of straight lines. The example provided is the cubic equation over the range x equals to -2 to x equals to -4. The video shows how you can draw straight lines to approximate the curve of this complex equation. The more straight lines you have, the more accurately you can approximate the curve. This leads to the idea that a neural network with the right activation functions can learn to approximate a complex continuous function by learning parameters for a series of lines. The question then becomes, how can we mathematically represent a series of lines that can approximate any continuous function? The video introduces the rectified linear unit, which is the ReLU, as a function that is useful for that purpose. Moving on to clip number 6, modifying the ReLU function.
Equal to z. And now do you see what's happening? I have added bunch of complex functions. These are all straight lines, right? Because r of minus x minus 1 is minus x minus 1. So these are all linear functions. And no matter whatever I do, if I add bunch of these linear functions together in whatever way we want by changing its slope, intercept, whatever, as long as it's a straight line, a combination of these straight lines will give me another straight line only. So if we don't have the ReLU activation function or any kind of activation function, we cannot represent nonlinear data using neural networks. This is why activation functions are so important. And I would even say it's the cornerstone of the whole idea of neural networks, that you can construct these piecewise functions and approximate pretty much any function that way. If you have discontinuous function, that is the reason why sometimes you have multiple hidden layers. So I hope this makes it very, very clear for you in a visual way the importance of activation functions. And r of z equal to z. And now do you see what's happening?
So for our last clip, is very interesting how it explains how different versions of the ReLU function can be constructed by modifying the sign of the function or adding a constant to the input. The video demonstrates how simple manipulations such as adding a constant to the input or multiplying the ReLU output by a constant results in modifications to the shape and slope of the ReLU function. By using a Desmos graphing calculator, the video shows how shifting, flipping, and changing the slope of the ReLU function can generate different shapes. The visualization makes it clear how flexible the ReLU function is in representing different piecewise linear functions, which is how neural networks can approximate a vast array of continuous functions. It also sets the stage to show how the ReLU activation function in a neural network is the key to its ability to approximate any complex function. And that is all, everybody. I hope you guys enjoyed the video. This is the first video of a series for the semester. Have a good one.